All right, so today we'll continue looking at polar coordinates, and we'll finish up everything that we're going to do in section 5.1 pretty quickly. There's not that much left. Okay, the last thing that we really didn't do yet is how we convert the other way. Okay, so we already converted from polar to rectangular. Okay, that's using these two formulas. Okay, x is r cosine theta, and y is r sine theta. All right, so now let's take a look at doing it the other way. All right, so Marquise, if you had a point in rectangular, what are the two things that you're given when you're graphing the way you're used to doing it? Yeah, you're given an x and a y. Okay, so they'll tell you those two. And if we want to write it in polar, Nick, what are the two things that you need in polar?
R and theta.
R and theta. Okay, so somehow we've got to turn an x and a y into an r and a theta. All right, so I've drawn a point, and I would know the x and the y. Okay, and I'm going to draw those in. Okay, that's the y. That's the x, and what I'll do is I'll make that something you can see a little better. So x is how far over you go horizontal, and then y is how far up. And you will know those two numbers. Okay, my radius is the distance from this point to the center. That's my radius. So if I knew x and I knew y, how do you think I could get the radius? Yeah. Yeah, and I'll write that down in a second. So if you want the radius, you could use the Pythagorean Theorem. Okay? And that's one of the things. And this is theta right here. All right. So the next thing you have to do is figure out theta, and you're going to know x, and you're going to know y. Jasenia, do you remember the name of the side that's right next to the angle? What do we call that side?
Adjacent.
Yeah, so this side is adjacent. And Nolan, how about the side that's farthest away from the angle? Opposite. Okay. Does anyone remember what trig function has opposite and adjacent in it? Tangent. So what I can do is write tangent of my angle equals opposite over adjacent. Now my goal isn't really to know the tangent of my angle. I really want just my angle. So something I could do on both sides to cancel out tangent and just be left with the angle. What could I do on both sides here? Can you just say it one more time?
Multiply each side by the inverse tangent.
All right, so you want to do inverse tangent. We just can't multiply, because multiplying we can only do with numbers. This is a function. All right, so what I'm going to do is just take the inverse tangent of that entire side. It's kind of like taking the square root of a whole side and take the inverse tangent of the other side. So now what happens is that inverse tangent and regular tangent cancel out, and I'm left with a formula for my angle. Okay, to find theta, it's the inverse tangent of y over x. Sometimes. So that formula will work fine as long as you are in one of these two quadrants. If you're not, we have to make an adjustment to it. Okay, so it's important that you know what quadrant you're in, because that's going to change your formula for theta slightly. If you're in quadrants 1 or 4, the formula is exactly what we just wrote. Okay, inverse tangent of y over x, that's perfect. Now, if you're in quadrants 2 or 3. That's the adjustment that you have to make. It's pi plus inverse tangent of y over x. If you're finding your angle in radians. If you're going to find your angle in degrees, then it's 180 plus. Okay, so you only have to do 180 plus if you're in the second or third quadrant. Okay, so in step 1, when I say to graph the point and determine the quadrant you're in, you don't have to graph it perfectly. Really, all you have to do is determine the quadrant. If you can do that without a picture, that's fine. The only time you have to graph it is if the directions specifically say graph the point. Okay, so determine your quadrant. Use either the first or the second formula for theta. But those two formulas still don't cover everything that could happen. What else could happen besides being in quadrants 1, 2, 3, or 4? There are other places you could be. Okay, so you could be on the origin. Where else? It's kind of in general, and it'll include what Katrina just said. Yeah?
On one of the axes?
Yeah, you could be on one of the axes. Okay? So if you're on an axis, you can't use one of these formulas. Okay? Let's look at why. Let's say you had a point right here. Okay, I don't know what the y value is. It's some y value. But I do know the x value. What's the x value of this point? 0. Does anybody see a problem with trying to plug in that into one of those formulas? What would happen if you did that? You'd be dividing by 0. Okay, so if your x value is 0, which it would be here and here, that's a problem. Okay, so if you're at one of these 4 points that I just marked, you just have to know the answer is either 0, 90, 180, or 270. Okay, how would you know? You just graph your point. Okay, so let's say you had the point -2, 0. That's right here. It's 2 units to the left. Right? And then you just have to memorize this is 0, 90, 180, 270. Okay? Just memorize where those 4 angles are. But for anything other than those 4, you can use the formulas I showed you. Okay, so that's how you find your angle. And then you find r using this formula. Okay, we mentioned earlier what this formula really is, something we already know. What is this formula with just different letters? Yeah, it's just the Pythagorean Theorem. X squared plus y squared equals r squared. And that works in any quadrant. Doesn't matter. Quadrants 1, 2, 3, or 4. If you are on an axis, you really shouldn't need this formula. Okay, because if you graph the point, let's say, I don't know, 0, 3. And I ask you what the radius is. Well, anytime that you move straight in one direction on an axis, you can just count. Your radius is 3. Okay, that's the distance from the point to the origin. The only time you need these formulas that I showed you is if you're in the middle of a quadrant somewhere. Then it's kind of hard to count how many units. Okay, so you need Pythagorean Theorem. All right, so let's try this one. I want to convert the point 2, -2 to polar. Now, what I always do first is I do it in degrees, and if the answer that they want is in radians, then I convert it after. Okay, and now technically, you can find the angle first, or you can do the radius first. It doesn't matter. You gotta do both. All right, so Jared, which one do you want to find first? Do you want to get the radius first? or the angle first?
Radius.
Radius, okay. So John, can you tell me how to set up the formula to find the radius?
R squared equals 2 squared plus -2 squared.
Yep, perfect. So you're just using the Pythagorean Theorem where the two sides of the triangle are both 2. Even though that's a negative, it doesn't really matter because when we square it, it's going to disappear. All right, so Brian, what's 2 squared? And a -2 squared? Yep, it's also 4. Mistake some people do there is they write -4. Don't do that. Okay, so r squared equals 8. And how about Jesse? How do I get r by itself?
Square root.
Take the square root. Okay, and we've talked a little bit about reducing square roots when we did unit circle trig and the distance formula. How does the square root of 8 reduce? 2 square roots of 2. Yeah, I will be looking for that step we just did. Okay, so make sure you reduce it if you can. Okay, so there's my radius. And now I need my angle. Paige, what should I figure out first that's going to tell me which formula to use for my angle? Yeah, I got to figure out what quadrant I'm in. And can you tell me what quadrant 2, -2 would be in? Which one? Yep, it's going to be right 2, down 2. So somewhere in quadrant 4. Now I'm going to look up my formula for theta in that quadrant. So Kyle, what's the formula for theta in quadrant 4?
Inverse tangent y over x.
Inverse tangent. And now just type y over x. And here the negative is important. Copy exactly what you have for y and x. Okay, so -2 over 2. Okay, so I'm really going to be taking the inverse tangent of what number? -1. Okay, and as I said, I always do it in degrees first. Okay, and I'll show you why. If you do it in radians first, you get that. Okay. Does anybody recognize what that is in terms of pi? It's not easy to recognize what that is because it's a decimal we're not familiar with. Okay. Let's do it in degrees first, and then it'll make that number a lot easier to recognize. Do it in degrees. It's -45 degrees. Okay, so I'm going to write my answer 2 ways. First, I'll do it in degrees. Okay, and I happen to do it with a positive radius and a negative angle. We talked about there's 3 other ways you could write this. You could do positive, positive, negative, negative, and so on. But I want to write it in radians as well. So in radians, my radius doesn't change, but my angle does. Okay, it's going to be negative something. How do you convert degrees to radians? If you didn't have memorized what 45 degrees is. Yep. Yep. So 45 will go into itself once, and it'll go into 180 4 times. So that number that I just showed you, that -0.785, that was the number negative pi divided by 4. Okay, so it's a lot easier to do it in degrees first than convert it, rather than trying to recognize 0.785 as a number. Okay? Yes?
On the test, do we have to do both, or can we just do one?
Nope, I'm just going to ask for one. But if it's multiple choice, you're going to have to, you might have to convert and figure out which one is correct. Now, let's look at this one for a second. What's another way I could write negative 45 as a positive angle? Just in case the answer on the test has a positive angle.
315 degrees.
Yeah, that's the same as 315. Instead of going clockwise, you can go counterclockwise. Okay, so any of the things that I circled, these are all correct. So you could write it in degrees, and there's two other ways we could write it in degrees too. I won't go through all four, but you could do it with the negative radius as well. And same in radians. You could take every answer you have in degrees, and you could change them to radians. Right, so there's lots of different ways you can write it. If the book doesn't ask, I don't care which answer you write it in. Just be familiar with the other ways to write it. Okay, so any questions on that one? All right, let's try one more of those, and then we'll move on to our last section. How about Shannon? What quadrant is this one in? -4, -5.
3.
Yep, it's going to be somewhere over there. It doesn't have to be exact, as long as you know it's quadrant 3. And Shannon, what's the formula for our angle in quadrant 3? And let's do it in degrees.
180 plus inverse tangent.
Perfect. Inverse tangent, and what did you say for that part?
-5 over 4, A4.
Okay, now, why did she add 180? Why do we have to do that this time? Connor?
They're in degrees.
Okay, so let me be a little clearer. Why do you have to add something to the tangent this time, whether it's pi or 180? Why not just do inverse tangent -5 over -4? Right, because you're in the third quadrant, so you have to add something. Just depends on what mode you're doing it in. But quadrants 2 and 3, you've got to add 180. All right, so this one's not going to come out as nice of an answer, so we'll just round it off. So 180, and then inverse tangent of, the negatives are going to cancel out, so you just type in 5/4. We get 231.34. And just do a quick check, make sure that makes sense. Okay, this is 180. That's 270. I'm supposed to be in the third quadrant, and yes, 231 is somewhere in the third quadrant. So it seems reasonable. Okay, and Katrina, what's the other thing I have to find? I've got my angle.
Radius.
Yeah, and can you tell me how I'd find my radius?
You do x squared plus y squared.
All right, so -4 squared plus -5 squared. And what goes on the other side?
R squared.
R squared, perfect. Okay, so let's do that out. We're going to get 16 plus 25. And Rebecca, if I add those up, what's 16 plus 25? 41. Good. And when I take the square root of that, is 41 a square root I can reduce? No. So we could leave it as the square root of 41, but since we already rounded our decimal, our angle off, why don't we just round the radius off? It doesn't make sense to leave one of them exact and one of them approximate. So let's just round this off. About 6.40. Okay, so my point is R comma, theta. Okay, questions on that? Okay, so that's changing from rectangular to polar. All right, so now we're going to come back to polar a little bit later, probably towards the end of class tomorrow. But for now, into the first half of class tomorrow, we're going to kind of switch gears and talk about complex numbers. Okay? And then we'll make a connection tomorrow and Thursday. So before we really start, I just want to make sure we understand where complex numbers kind of fit into the big picture. All right. So what I'm going to do is I'm going to start with the simplest kind of numbers we have, and then work my way out to more complex ones. So the simplest kind of numbers that you have don't include 0, and they start with 1. No negatives, no fractions, no decimals. This is 1, 2, 3, 4, 5, 6, 7, 8. That's an example. What was I just doing as I went like this? Counting, yeah. So those are your counting numbers. Okay, but the problem with counting numbers is you could run into a situation with arithmetic where you don't have an answer. Actually, a few different situations. Can anybody think of some operation you could do with arithmetic with counting numbers where the answer would not be a counting number? Where counting numbers are just 1 and up. So is there anything you could do arithmetic-wise? And don't even think multiplication and division. Just think addition or subtraction.
0 or less.
What'd you say?
When a number is equal to or less than 0.
Okay, so give me an example of a problem you couldn't do if all you understood was counting numbers.
1 minus 2.
Yeah, 1 minus 2 definitely doesn't exist. Even 1 minus 1. Okay? If all you understand is counting numbers and I ask you to do 1 minus 1, you'd have to say this is undefined. Because we don't even have anything that exists to represent that in counting numbers. Okay? So that's where the next set of numbers comes in. Okay? And those are whole numbers. That handles this problem right here. Now we've just basically invented the number 0, or the idea of nothing. All right? So now we can use any number from 0 and up. So addition would work fine. You could always add 2 whole numbers and you'd never have a problem. But how about subtraction? Could we run into a problem subtracting 2 whole numbers? Somebody give me a problem you can't do if all you understand is whole numbers? Sam? 2 minus 3. Yeah, you can't do that. Right? You're trying to take away more than you have. That's impossible. Right? So if you don't understand the idea of negatives, you'd have to say this is undefined. Right? Unless we invent a new kind of number to represent something less than 0, and that's the kind of number that has that symbol in front of it. Right? Meaning your negatives. Okay? So those are, does anybody know what those are called? Yeah?
Real numbers.
Not yet. Real numbers are going to be this whole left-hand side of this diagram. That'll be the big picture, but we're going to get to those.
Are they integers?
These are called integers. So now with integers, you can use negatives, and that would handle this problem. But we could still run into some problems. Not with addition. Adding integers is fine, subtracting them is fine, multiplying them is fine. But somebody give me a problem you can't solve with just integers. What don't integers include? Yes? Okay, they don't include square roots. Think even simpler though. Not quite. We're going to get to square roots in a second. What's that? Decimals and fractions. So what's a problem you couldn't do with integers if you don't understand decimals and fractions?
2 divided by 3.
Yeah, you can't do 2 divided by 3. Okay, if integers is kind of the extent of what you understand, you'd have to say this is undefined. You'd have to say you can't do that. How do you take two objects and divide them between three people? You can't do that evenly. So that would be undefined. Unless you want to invent another new kind of number. And that's where we get parts of things, okay? Fractions and decimals. Okay? And those are rationals. Okay? So now rationals let you do things that are not integers. Okay? You can take parts of numbers. And I'd say for probably everyday kind of purposes, rational is probably as complicated as you need to get. You know, if you're cooking, for example, you might use 2/3 of a cup or a quarter of a cup, things like that. As we start to go beyond rationals, now the numbers are getting more theoretical. Right? And not used as much in kind of everyday simple stuff. So this left-hand side, those are my rationals. Does anybody know what other numbers are the opposite of rationals? Sam?
The imaginary one?
Not yet, but those are going to be up here in a second too. Yep.
Irrational?
Irrational. Okay, so irrational numbers are numbers you can't write as a fraction. Right? And that's kind of a complicated idea. Right? Think like if you're, let's say, you do simple kinds of things, thousands of years ago, you understand, all right, you could take like a piece of wood and cut it into 3 parts, and then maybe you could give 1/3 to someone and 1/3 to someone else. So you understand basic fractions. But the idea of having numbers that you can't write as a fraction, that didn't make sense to people. Like they didn't understand why would you ever have things that can't be written as fractions? Until they started to understand numbers like pi. Okay, pi is a number you can't write as a fraction. Square roots. Okay, those are also numbers you can't write as a fraction. I could prove to you that the square root of 2 can never be written as a fraction. From now until forever. We will never be able to do that. I can't do that with pi. We don't really know yet if pi can be written as a fraction. They've checked a lot of digits of pi, and they know for as many digits that they've checked, you can't do it. But they still haven't come up with a way to actually prove it, other than just checking tons of digits. All right? But again, these kind of numbers are more complicated. You don't use pi usually in your everyday life. You might use it a little bit if you're in certain fields that have to do with circular things, measuring circles or stuff like that, but most people don't use the number 3.14 in everyday life. Okay? So uses are getting more complicated. And then somebody mentioned reals. Together, all your rationals and irrationals make up your real numbers. Okay, and I should have probably mentioned earlier why you need irrational numbers. Because if I gave you a problem like this, and I said to solve it, well, if all you believe in is fractions, you're never going to solve this problem. Because the answer is not a fraction. Okay, it's the square root of 6. Listen. Okay, so that's why they had to invent another new kind of number. And that's where rationals come from. A number you can't write as a fraction. But there's still a problem that we can't solve. And it does have to do with square roots. X squared equals, whoops, just write -4. What's wrong with that? What happens if I try to solve that with my real number system? Okay, let's pretend that's what I understand. So we know up to algebra 1 now. Yeah.
We would get imaginary numbers.
Yeah, you get an imaginary, because this is saying multiply 2 numbers together to get -4. And the 2 numbers you multiply together have to be the same. So there's 2 ways you can do that. You could multiply a positive times a positive, or you could multiply a negative times a negative. I don't care which way you do it. You're never going to multiply 2 numbers that are the same and ever get a negative. So if all you understand is real numbers, then you'd have to say this is undefined. Right? Or in Algebra 1, before if my students understand that kind of problem, if they come across it, I say just write undefined. You can't do it. Right? And same thing on the calculator. If you try to type it in, calculator gives me an error. Now, technically it's not undefined. Okay? You can figure it out if you're willing to invent another new kind of number. So that's basically what we do. Every time you have a problem you can't solve, they invent types of numbers that can solve it. And that's not our real numbers, but getting into imaginaries. So now, by changing the mode to imaginary on the calculator, it's like I just taught the calculator Algebra 2. Now it doesn't say error anymore. It just invented a new kind of number to solve it. Okay, imaginaries. Okay, so over here are your imaginaries. And together, all the reals and imaginaries, those are called complex numbers. Okay, so complex numbers, those are the big picture. And what I do to sometimes try to understand it is I think of these as places. Okay, think of counting numbers as like Boston, whole numbers Massachusetts, integers, the Northeast. Okay. If you're a whole number, you're automatically a counting number. Okay, that's like saying if you're in Massachusetts, I'm sorry, other way around. If you're in Boston, you're automatically in Massachusetts. Okay, so if you're a counting number, you're automatically a whole number. And if you're within Massachusetts, you're automatically within the Northeast. So if you're a whole number, you're automatically an integer as well. Okay? But look at it the other way. If you're in the Northeast, are you automatically in Massachusetts? No. So just because you're an integer doesn't automatically mean you're a whole number. It doesn't work that way. Okay? So it kind of works from the outside, or I guess inside working out. Okay? If you're something on one of the boxes, you're automatically everything outside of it as well. But if you're outside of it, you're not automatically what's inside. Okay? And for our purposes, we're just going to study very basic operations with complex numbers. We're not going to do word problems. We're not going to look at applications. Because now if you want to start asking where are complex numbers used in everyday life, now you're asking about things that probably less than 1% of people actually do. So that's why we're not going to focus on applications. Because it's probably not something you're going to do unless you're an engineer. Okay? Or you take calculus, and that would also probably be for some engineering. All right. So I just wanted you to understand kind of the big picture and very, very basic things, like how to add, subtract, multiply, and divide. And that's all we're going to do. Okay, so any questions on that? Okay, so there's our number system diagram. So complex numbers are usually written in this form. Okay, I don't know if you noticed it when I changed the mode on the calculator, but it said A plus BI on it. And that's exactly the way our textbook describes writing a complex number. Okay, complex numbers have two parts, just like you saw in the number diagram. They have a real part, which we put on the left, and an imaginary part, which you put on the right. If you write it exactly like I've shown you right here, that's called standard form. Okay. There's an example of a complex number in standard form, 2 plus 3i. Don't write 3i plus 2, okay, if they ask for standard form. So in that number, it has two parts. It has a real part, which is A, and an imaginary part, which is B. The I is just there to tell you what's in front of it is the imaginary part. Okay, so B is the imaginary part. Shakira, what's the real part in 2 plus 3i? 2. And the imaginary part? 3, exactly. Does everybody have everything above 2 plus 3i? Okay. Now, sometimes one of those parts could be 0. Okay, and in fact, for numbers you work with in Algebra 1, the imaginary part is always 0. Okay? We normally don't write numbers like this in Algebra 1, but let's say you did this problem, 2 plus 3. You could write the answer like that. It's 5 plus no imaginary part. If there's no imaginary part, why bother writing it? Okay. So in that case, okay, when I did this 2 plus 3 and I wrote 5 plus 0i, 5 is what we call, it's just a pure real number. It's a number that has no imaginary part. Now, let's say you switch that around. Okay, write down a number that doesn't have a real part. Then that's called a pure imaginary number. You could write something like this. 0 plus 6i. No real part, just imaginary. Okay, I will tell you though, in general, if you look in the book or on the test, if something has a 0 part to it, they're just going to leave it off. So those three expressions are all examples of pure imaginary numbers. Any questions on them? And if you have a graphing calculator, you can type things in. Like the calculator can do a lot of these things for you because it has a button on it for I. Okay, I haven't even really talked about what I is. Okay, I will at the very end. Right, so the next thing the book explains is what it means for two complex numbers to be equal to each other. All they're really doing here is emphasizing that complex numbers have two parts to them, a real part and an imaginary part. And in order for two complex numbers to be equal, both the real parts have to match and the imaginary parts have to match. Okay, so that's all they're really emphasizing is complex numbers have two parts to them and they both have to match. Okay, so there's an example, very straightforward, of two complex numbers that are the same. The real parts match, the imaginary parts match. Now, if I did something like that, those complex numbers are not equal. Part of them is, okay, the real part matches, but the imaginary part does not. Okay, so just don't forget complex numbers have two parts to them. Okay, that's kind of the important idea there. Okay, so the last two things we'll look at for today is how do we add complex numbers and how do we subtract. We'll save multiplying and dividing for tomorrow. Does anybody know how you add complex numbers? Like if I wanted to add these two together, how do I do it? Yeah, Connor?
Can we go the real parts and the imaginary parts together?
Yeah, exactly. You combine the real parts together. Okay, think of those as like terms. And then you combine the imaginary parts together. So the real part is the A and the C. And the imaginary part, that's the B and the D. Don't forget to put the I after that so we remember that's the imaginary part. Okay, so let's try adding those two complex numbers up. So it says 3 plus 8i plus 8 plus 2i. So Sam, if I add these together, what's the real part going to be? Yeah, so the first one has a real part of 3. The second number has a real part of 8. Combine the real parts, and you get 11. Okay, and Selenia, what's the imaginary part in the first number? 8. And how about the imaginary part in the second one? 2. And then add them up. 10. And what do we put next to it? Perfect. Okay, this is the section where you really want to make sure your ones and i's look good. Okay, that's it. 11 plus 10i. Okay, try 1b and 1c. Okay, on your own, take maybe 30 seconds. Do those, and then we'll take a look at them. Okay, so Jacinia, can you tell me what you got for the real part on 1b?
7.
Yep. And how about the imaginary part?
Minus 10. I.
Perfect. Yeah. So 4 plus 3 gives you the 7, and then negative 2 plus negative 8, there's your negative 10, and don't forget the I next to it. Okay, as I walked around, some people had a plus 10i. Okay, just be careful with that. Okay, and we'll finish up addition looking at 1c. Okay, Shannon, what did you get for the real part here?
Negative 10.
Yeah, negative 3 plus negative 7 is negative 10. That's good. And how about the imaginary part?
Plus 4i.
Perfect. Okay, so any questions on addition? Okay, because if you understand addition, subtraction is very, very easy. Okay. What you're doing now is instead of adding the real parts and adding the imaginary, you are subtracting the real parts and subtracting the imaginary. Okay, and what you have to remember that sometimes people forget is it's A minus C. Okay, so the minus gets distributed to the C, and it's B minus, B minus D. So the minus also gets distributed to the D. Both the C and the D are subtracted. That's a pretty common mistake. People forget to subtract both. Okay, so we've got 4 plus 12i minus 3 plus 4i. So the first thing I usually do, just so I remember, subtract the 3 and subtract the 4i. Okay, so Skylar, what will I get for a real part when I subtract here?
1.
Yeah, 4 minus 3. 1. And Connor, how about for my imaginary part?
8.
Yep. 12 minus 4. So that's 8. And what do I put next to it? I. Okay, any questions on that one? Okay, and last one for subtraction. 3 minus 5i minus 8 minus 6i. Anyone think they can tell me the whole thing there? That's the final answer. Shakir?
5 minus 11.
So you said 5 minus 11i? All right, let's check it. So the first part, 3 minus 8. Well, if we did 8 minus 3, that would give us 5. But anyone want to just change something, small change there, because we do 3 minus 8, Sam? Right, so negative 5. And how about the negative 11i? I definitely see how you got it. You did negative 5 minus 6. But here we got to be careful. It's negative 5 minus 6.
It's just I.
Right. It's going to turn into negative 5 plus 6 because you're going to subtract a negative. Okay? And as John just said, negative 5 plus 6, it's just plus I. Okay? If you wanted to put a number in front of the I, you could. It's invisible, but what number is there? You could put plus 1i. If it was multiple choice, that's how I would write it. All right. So I said I was going to kind of explain what I was. It's kind of the last thing, and this will lead us into tomorrow. So I is the square root of negative 1. I can't explain to you why that's true. I can't come up with a proof for it. It just, that's what it is. I is the square root of negative 1. It's kind of like in geometry when you say parallel lines don't cross. You can't explain why. It just, that's what it is. Parallel lines don't cross. That's how you define it. And from that fact, you can do other things in geometry. Same thing here. I equals the square root of negative 1. It just is. That's what it is. So from that fact, we can figure out other things like I squared. Right? So if I is the square root of negative 1, that's I. What do you get if you take I and square it? It's the square root of negative 1 squared. Okay.
So like I squared?
Yeah, this is what I wrote right here. This is I, and I'm squaring it. What would that come out to?
Negative 1.
Yeah, this would come out to negative 1. Okay, and that's important because when we get into multiplication tomorrow, I squared is going to come up a lot. So what we just saw is anytime you have I squared, it's equal to this number. You can double check on your calculator if you have one like this. So anytime you see I squared, we're going to change it to a negative 1. Okay, and we'll pick up with that tomorrow. Okay, so the homework, the first part is on the polar, okay, converting between rectangular and polar. That's 308, not 208 or 209, but 308. 55 to 65 all. And page 560, 9 to 14 all. That's adding and subtracting.